Going now to the last part of our discussion on angular motion, after which we'll go over the examples part. We have second condition of equilibrium. In our discussion on force and motion, in our discussion of motion in a straight line, basically, we had the first condition of equilibrium. That's for motion in a straight line. For angular motion, we have the second condition of equilibrium. An object or system is said to be in a state of rotational equilibrium or angular equilibrium when the net torque experienced by the object or system is equal to 0. Net torque is equal to 0. This is the second condition of equilibrium. And net torque, second law of motion for rotational motion or angular motion, net torque is equal to I alpha, wherein we set the moment of inertia I to constant. If the net torque is 0, that means acceleration, angular acceleration is 0. The rate of change of angular velocity is 0. That means the angular velocity is not changing. The angular velocity omega is constant. A system that is in equilibrium is characterized by constant angular velocity. If the angular velocity is constant at 0, the object is or system is in a state of static equilibrium. On the other hand, if the angular velocity is constant at a non-zero value, that means the object is moving at constant velocity, the object is said to be undergoing uniform circular motion. An object is in a state of total equilibrium if it satisfies both the first and second conditions of equilibrium. Again, first condition of equilibrium, we covered that in our discussion on force and motion. F net is equal to 0. The net force is equal to 0. That's the first condition of equilibrium. And the second condition of equilibrium, we have torque net is equal to 0. For a system or object to be in a state of total equilibrium, F net must be equal to 0 and torque net must be equal to 0. If the object or system only satisfies one of these conditions, for example, if F net is equal to 0 but torque net is not equal to 0, then the system is equilibrium only in the linear motion. It only satisfies the first condition of equilibrium. If F net is not equal to 0 but net torque is equal to 0, then the system or object is only in equilibrium state in the angular motion. It only satisfies the second condition of equilibrium. Total equilibrium, the system must satisfy both first and second conditions of equilibrium. Again, it must satisfy both F net is equal to 0 and torque net is equal to 0. If an object or system is not in equilibrium state, then it is considered to be an accelerating system. We use second law of motion. Again, for constant moment of inertia I is equal to constant. Second law of motion tells us net torque is equal to I alpha. And that's basically how we analyze torque and motion. We need to determine if it is in equilibrium state. net torque is equal to 0, or if it is an accelerating system, net torque is equal to I alpha. Very much like what we did in force analysis. In force analysis, you will recall, we either set the net force, F net, to either 0 or MA. For angular motion, for torque and motion, we either set the net torque to 0 or we set it to I alpha. And that's pretty much how we do force or torque analysis rather. First things first, of course, look at the problem, draw the system or object. If the object or system drawing is not provided by the problem, then using the drawing, identify the forces present in the system. In knowing the forces present in the system, you have an idea of the torque experienced by the system. Then, using either net torque is equal to 0 or net torque is equal to I alpha, you analyze the torque present in the system. Similar in steps basically to our net force analysis. So if you know how to do net force analysis, you basically have an idea on how to do torque analysis, how to analyze the torque and motion of an object or system. And some last notes before we finish up this video. In the previous videos, we mentioned that it's very easy to remember the equations of angular motion. That's because most of these equations follow the same equation form as those in linear motion. For example, compare your linear kinematics, your motion in a straight line kinematics, with your angular motion kinematics, and you'll see the similarities in the equation form. The same goes for most of your dynamics equations in angular motion. All you need to do is remember the equations of linear motion and then replace the variables with their angular counterparts, and you have the equations for angular motion. Just get the equations for your linear motion and replace the variables with their angular motion counterparts. Replace x with theta, replace v with omega, a with alpha, replace m with I, f with tau, and p with L. You have your angular motion equations. So again, it's very easy to remember the equations of angular motion for the most part. That is to say, as long as you remember your linear motion equations. Of course, you can always go about it by rote memory. If you have no problems memorizing the equations for linear motion and the equations for angular motion, then do so. But if you have problems memorizing too many equations, just take note of this. Just remember your linear motion equations, and note that many equations in angular motion follow the same form as their linear motion counterparts. And that's it for now. We'll continue our discussion on angular motion. We'll finish up our discussion on angular motion in the next video, wherein we take a look at a few examples. So once again, that's it for now, and thank you for watching.